Good morning, good afternoon, good evening, everybody. Welcome to the December edition of the IREE Community Meeting. Today we have a couple of topics. One on vector layout analysis and some of the work that and Pathfinder has been going on in that regard. And then we have a discussion on all the different GitHub organizations and repos and pain points and joys they bring. But I think I'll sort of kick us off then with handing it over to Kumar.
Hello, I'll just share my screen and then we can get started. I have some slides. So, let me know when you can see my screen and the slides.
We can see your slides.
Okay, so I'll start. So hello everyone, I'm Kuar and I'll be presenting the work me and Harsh have been doing during the past 2-3 weeks on ramping up like vector distribution to get distribution for things like flash attention and reductions. So first let's try to understand some of the problems that we face currently with the vector distribution that MLR has. So this is an example and which is in SIMD world right now, and we want to put it into SIMD world, which essentially means you distribute it like workload to each thread. So how you do it today is you just wrap it in an execute on lane 0 operation. You just say, hey, all of this work is done by thread 0 now, and this isn't now distributed, and you try to remove operations out of it one by one. So when you remove something out of this lane 0 region, you just say it's distributed now. And this is how things are done today. And so if I just take this example and put it into vector distribution today, this will fail because it will tell me that, oh, I'm trying to distribute a vector of 4 into F16. Well, I have 64 threads on some AMD GPU, and it says, well, I can't distribute that, so I'll just quit. And it fails, and you're executing things on only thread 0 now. It's really bad. So let's give it a chance to actually distribute things. We'll say our vector is 128 into 512, and we are doing a reduction on that, and we're trying to write it on that. So I'll try to distribute this 128 into F16. It will actually distribute it across 64 threads. So you get vector 2 into F32. And now you will try to distribute multi-reduction. So it always takes the last stop or whatever is yielding out of the execute lane 0 region. And now the thing is that what comes is you already distributed the transfer right. Now, when you're distributing the reduction, the only thing that you know about there is the reductions type, like what is its shapes, and what are the number of threads you have available. You don't know how you distributed transfer right or anything. So here, first one thing is this restricts what you can do, and the current distribution only handles 1D vectors. So what you would do is you take this 128 into 512 vector, you'll split it into 128 reductions, and then you will distribute each reduction, each row in a reduction completely. So you'll completely distribute them, and then you will try to write them. Now, this has a couple of problems. One problem is that usually since you have multi-reduction, you'll try to pack 2 rows if they're F16 into F32s, and you'll try to optimize the number of shuffles. This was something that Github was actually trying to do with the current vector distribution, and it inherently was really, really hard to do. He did a lot of hacks. He tried to get it up. This example was something he was trying, and this was hard. So, and another thing is, if you look at this, so different colors represent different threads. So in this 128 reductions, it just happens to work because when you reduce, each thread actually gets the reduction. If we're assuming it does some XOR reduction, so each thread gets it. And because the transfer right is distributed each, in this 128 threads, each thread writes to 2 locations. So if this whole broadcasting thing was not true, everyone not getting the same values, this wouldn't work. So, but that's an aside. So, but the problem is let's say I want to use some different layout for reduction, something like Github was trying to do. He wanted to pack 2 rows together and do it in batches. So I cannot tell the distribution in any way that, hey, I want to use this. So how do I say that? So to counter this problem, this actually arises a lot in something like flash attention, where my instructions, I want to give them, they have their matrix multiplication instructions. For different GPUs, I want to tell them, hey, you have like this column, you have row major distribution as inputs, but your output is a column major distribution, something like that. And NVIDIA has its own layouts. So there's no actual way to tell it. So what we do is we first introduce a vector layout analysis. And what it does is you take some values in your IR and say they're anchors, and you assign a layout to them in this analysis. So it gives you an interface to, it gives you like a user interface where you can say this value now has this layout. And the layout is just an attribute which implements the vector layout interface. That's on you how you want your layout to look like. You could implement a cutlass layout. You could implement a very simple layout. I just implemented the previous layout that IREE was already using, some high dimensional layout that we call it. So once you give it that, it has some transfer functions. It'll run a data flow analysis and just give every value that it can a layout. And now distribution is easier for you because now you don't have to infer anything. You don't have to think of how you're going to actually distribute the vector. Now you just need to know this is the distribution layout that I'm assigned, and this is what I'm asked to distribute. Now, if someone asks me 2 packed rows, then I'll do it because that's just what I'm supposed to do. I don't have to make a decision in the code gen. So these are like separation of concerns, and you get a lot of user input in this. So we, instead of just writing it as like a whole canonicalization or like moving them one by one, we write distribution patterns. So if you have a multi-reduction, you can distribute it independent of anything else. So sorry, this should be a SIMD to SIMT conversion. So what you do is you take, you have this original operation. You, on its operands, you can call get distributed, which would say when this value gets distributed, what would be its SIMT counterpart, and it'll give you some value. You don't care how it gets it, you just get the value. And that's how like you can get any values SIMT counterpart. And when you're actually replacing something, instead of rewriter.replace, you just use replace OP with distributed values. So you get the old reduction, replace it with your new SIMT operation that you have written, and you replace it. And it will internally just like handle everything, all the analysis updates it needs to do, all the like distribution updates it needs to do. That's on it. So this is just like you write localized patterns and you have global analysis. So it makes things really, really easy to write. I had to rewrite a lot of stuff, and it helped. So how it actually works inside is that there are 2 SIMT and 2 SIMD operations. So if you know like bufferization and stuff, there's like, it takes inspiration from there, that you have 2 tensor and 2 memory, and in the end they all just like they all just like fold, or there are some dead ops. And this is what happens here also. When you finish your SIMT or SIMD conversion, they all fold away or something like that. So this introduction of 2 SIMT and 2 SIMD ops also allows you to like compose it with any other distribution strategies. So I remember like when we were discussing this earlier, Quinn asked me like, sometimes we do a distribution like scf.forall, and it's just like blocked simple distribution. How would this compose with it? Like, is it like one, just like you take one thing or the other? So what you could do is like you just mark these ops that is already SIMD. This is SIMD. You convert this for me, and it'll just compose with it. So that was like how the thing works. And there are like, I'll talk about some details, like some internal details. So sometimes when you are doing the vector layout analysis, you can get layout conflicts. So your transfer read says that, hey, I'm going to read in I'm going to read 8 elements in a time, and I have a batch size of 2. But your matrix multiplication instruction says I can only take 4 elements at a time. So it'll just insert a layout conflict resolution operation between those 2 vector types. So I'll create a new vector type and give the resolve type, and the conflict type will be still the same of the operation that's producing it. But they have the same vector type, but they have different layouts now. So the MMA op is still getting the 4 read values it wanted, and the transfer read it's still producing, let's say, 8 values. And these resolutions can be handled at the time of distribution. So something like this 8 and 4 would be handled by you take those 8 elements and convert them into 2 batches. So you can do that at time of distribution. That's not the analysis concern. So there's something that we have, and it helps a lot. Like there have been like we were trying to debug flash attention, and there was like a number of times where I just looked at the analysis result and we're like, oh, there's a conflict op, we messed up something. Sometimes we need a conflict op also. So that's about conflict ops. Another thing is we talked about SIMD to SIMT rewrites. There's another class of like for SIMD to SIMT, it's easy because when you create, what you'll be doing is you're creating new SIMT values, and they don't need layouts now. So you just create them and replace them, and it works fine. It's easy. But what like problems happen when you try to do a SIMD to SIMD layout rewrite? So for example, how sometimes you don't know how to like, what do I do with this conflict? I have no idea how I can resolve it. So there's a default resolution, which is just you write to shared memory with your source layout and read using your desired layout. And that'll always work because you just like all threads write, you have a barrier and then you read it out. So that'll work. But it's doing so will require you to like when you create these write and read, you have to tell the analysis, hey, this new operation has this is using these values and it has this layout, and the layout analysis just has to trust it, because if you keep on running the analysis side by side, it may cause destructive, like it may not even work properly. So there are like other cases where you may need to do SIMD to SIMD rewrites. One is that let's say there's a conflict which is a transpose, like you move from a row major to a column major distribution, and you just want to propagate that transpose down, so like it fuses with some, let's say, transfer right. And you can it's really hard to do that because you'll have to go to the analysis and do like override that your layout is now this, but it's a data flow analysis, it's at fixed point. So the only modifications we allow is like addition of operations. It's hard to change the analysis of something. So with this like in mind, like this is a problem that we face, and there's future work plan. So we're upstreaming this to IREE first, and there's an analysis patch up. There's a lot of distribution work we have also done, which we will be upstreaming. For mostly, we're trying to get flash attention to working first as a like test that it's one of the hardest cases according to us. And there are like other things that we would want to do. One is like discussion Harsh started upstream, that having explicit layout vector types. So when I do a SIMD to SIMD rewrite, I would love to have these explicit layout vector types, because then I don't have to update our analysis. Analysis just like propagates some like initial types, and then I can do whatever I want because each operation is carrying the layout analysis type. And currently I'm just like in each value, I just assign it in the analysis. And other two things that I wanted to try is like, can I do the analysis in such a way that I get the least possible amount of conflicts? And what would be the best layout to use? Is it like Cutlass is a cute layout? Is that the best layout we can use? Or can we use a block layout? Or can we use a very simple layout? Or should we use different layouts for different kind of instructions because they're easier to do? So yep, that's all I had. Yeah, I'll take questions now.
Very nice. So, I mean, some of this also sort of reminds me on some of the layout analysis in XLA, and I mean, I'm sure like a lot of the frameworks have like similar things. With respect to like the propagation and like the constraint systems here, you know, basically, like what restrictions do you have in the layouts? Like, what is your starting point? Is there certain constraints that have to be maintained, or is this, you know, is this for performance and you're free to assign any layout that you want, kind of thing?
So basically how the layout analysis works is that you at start tell that these values have to have these layouts, and that's an anchor. And then operations have some transfer functions. So they say like there are two kinds of transfer. One is I call propagation and one enforcement. Probably they'll change. But propagation types is like they update result value layouts. So you take some operand layouts, and based on that, you infer a result layout. And similarly, there's enforcement, something I call, and based on result and other operand layouts, you find an operand's layout. So it's inference. Like I wrote these transfer functions, and for something like element wise, let's say, if you already know if there are two operands coming in, then the result should have the same layout because it's an element wise operation. And if you have a result, then you would try to keep both operands layout same as the result. Things like this.
And so you mentioned the anchors. Is the anchors purely specified by the user, or
By the user.
Okay, and basically, how does the user decide these? I mean, like, is this?
So there is, for instructions like matmul, there are already predefined layouts like MMA sync, MFMA, and WMMA already have predefined layouts. And for reductions, there are like you would have like some commonly known nice layouts. Like usually, if there's a matmul and a reduction, the matmul will provide layouts to everyone. And for a reduction, you would choose something nice that is known to be nice, or like a good default. And for reads and writes also, sometimes you have nice layouts. So for AMD GPUs, I know that you can load 8 elements at once, F16s. So you would want those layouts as anchors. So something like that. But it's all user defined, or like some kernel config kind of thing. Yeah, I'm not looking at the queue, so like someone could manage that.
Yeah, I think I was just asking. So it's more when you say the user, it's the user of the analysis and the passes. Not exclusively, from the user, whoever programmed it, because you're mixing in at that level hardware constraints and biases, and the user of the analysis in the system is saying, here's the ideal situation.
So I wanted so there was always like that you would have some default, as the person who's writing the passes would write some defaults, and like something like transform dialect could override them if you want.
Right.
Those. Yeah. Diego?
Yeah, thanks a lot for the presentation. I think I have a much better understanding now. I've been following all the discussions happening upstream. So I'm wondering, looking at the proposal, if this is something that we could model using specific operations to change the layout instead of changing the type. And also wondering, how much are we turning a vector type into a tensor type or a memrep type with this layout information?
Right. So this talk wasn't really about the explicit RFC, but I was like, this would be something nice to have. I don't think this I think that's a more broader discussion. So yeah, I'm not sure if I'm the best person to ask those things, but it was more something I would like to have them if I could have. So
okay, yeah, we can have this discussion, I think, on Thursday. We're planning to do that. Okay.
Yeah. I can tell everyone is scared of that thread. Let's talk about it on Thursday. I don't want to talk about it now. It'll be fine.
Go ahead, Manish.
Yeah, so I joined in middle, but you mentioned Qt layout. So is it the Qt library from NVIDIA that you were talking about?
Yeah. So yeah, that was what I was talking about. So this Qt layout could if I wanted to try that layout. So like if it can, I can add it as an attribute which implements the vector layout interface, the analysis would accept it and I could do distribution based on that. So that's something I want to try, but
So Qt layout, it basically provides you layouts and algebra on layout. So you can compose two layouts, you can divide layouts, you can tile layouts. So layout is a type in there. So what do you mean you want to try it? So you want to implement Qt in MLIR?
no, like, so like, I'm not sure if it's exactly Qt. Like, so there's, I think, a Graphine IR paper, and they use something very similar to Qt as a layout type. And I wanted to like try that because it seems like a very, like, I know like you have like very nice properties over that layout, and I wanted to implement as an attribute. So like I can use that for distribution. I wanted to like, I don't know if it'll work or something. So
I think to me, it makes sense to be more than an attribute. It has operations on the layout. So yeah, layout being a type and then operations on the layout to transform it and have some properties to check
so
on that. I mean, that's just me thinking out loud. Yeah, so thanks for the answer.
yeah. So I do want to have those like things algebra that you say, but like as C++ functions not exposed in the IR, because I don't see it right now how I would use it in the IR, like how it would benefit me. But like as I think the properties are very useful, and I think I would implement them as just like C++ functions or like the attribute, something like that.